Hi, I'm Ryan from the Technical Support Training Team, and today I'll be walking you through the fundamentals of wireless networks. When deploying a wireless network or making changes to an existing network, there are many factors to consider. This can be a complicated process, but if you understand these topics, you'll be well prepared in the field. We'll be covering wireless bands, network requirements, site surveys and heat maps, and some additional considerations. Make sure you refer to the resources linked in the description for in-depth information about all the topics we covered. Let's start with wireless bands. The most common wireless network can function using the 2.4 GHz and 5 GHz bands. 6 GHz is also possible with Wi-Fi 6E, which is relatively a new standard. As such, most wireless devices do not support this. Wi-Fi 6E APs are generally backwards compatible, as long as they are broadcasting 2.4 or 5 GHz SSIDs. It's important to understand the attributes of the bands, as there are pros and cons in each environment. All wireless bands are prone to interference with the environment like solid objects and other radio frequencies. 2.4 GHz frequency can better penetrate materials than higher bands, so it's able to achieve a longer range in areas containing solid objects. It's a more commonly shared band, so access points aren't the only devices using it. Cordless phones, microwaves, and other devices also use this band, so they can cause interference on a 2.4 GHz network. This frequency band has 11 different channels which data can be transmitted on, but only 3 channels are non-overlapping. This means these are the only channels we can use without running into channel overlap issues. We'll talk about channels shortly. Finally, 2.4 GHz generally has the slowest speeds of the 3 bands. The next frequency band option is 5 GHz. The waveforms are higher in frequency and can utilize wider widths, with less overlap and channel interference, meaning generally faster speeds. However, higher frequency waves penetrate objects less effectively and are more prone to signal degradation. 5 GHz offers up to 24 non-overlapping channels, so there are many more options to choose from. Because of this, its channels are less prone to congestion due to high traffic or interference with one another if multiple access points are close together. Not all devices support 5 GHz, so make sure to evaluate your client device requirements and your access point capabilities before selecting a band to use. The most recent commercially available frequency band option is 6 GHz for devices supporting Wi-Fi 6E. This band is the least prone to channel interference out of all the 3 options, but provides the least amount of coverage. 6 GHz has anywhere from 7 non-overlapping channels with 160 MHz width to as many as 59 non-overlapping channels using 20 MHz. The most common channel width is 160 MHz with 7 non-overlapping channels. You can take advantage of wider widths due to the frequency length. In the future, Wi-Fi 7 will be able to utilize widths of 320 MHz, producing an overall theoretical throughput of over 40 gigabits per second. Even more so with 5 GHz, the 6 GHz band is not supported by most devices. So again, evaluate your environment before selecting a band to use. Out of all 3 bands, it has the least channel overlap with wide ranges, meaning it has the highest throughput to interference ratio. We'll cover this in more detail when we discuss network requirements. Now let's talk about channels. This is one of the most important and often overlooked concepts when it comes to wireless technology. Misconfiguring a channel is an easy way to cause performance issues and instability. More information on channel planning tools and optimization will be discussed later. A frequency band is divided into segments or channels that can be 20, 40, 80, or 160 MHz wide, depending on the band. A single channel overlaps with other adjacent frequencies, creating potential noise and interferences which can impact wireless performance, referred to as adjacent channel interference. For example, you might be running 2 APs on 2.4 GHz, one on channel 1 and one on channel 4. Since those channels overlap, the signals will interfere with each other. In this situation, it would be best to select non-overlapping channels for each access point. Channel 1 for the first AP, channel 6 or 11 for the second AP. For this video, we'll be focusing from a North American perspective. However, in most other countries, channels 1 to 13 can be used, and even some up to channel 14. So please refer to your local regulatory laws for more information as the available non-overlapping channels may differ. We'll keep our focus on the 2.4 GHz band to help explain the concept further and keep things simple. Let's take a look at 3 wireless access points. If all 3 access points were using the same channel, this would be suboptimal as it can cause what's known as co-channel interference, or CCI, as each AP would be competing to communicate over the same frequency. When this happens, your Wi-Fi can range from slow to completely unusable, even though your devices shows as fully connected. In this case, it's best to switch each access point to different non-overlapping channels. This is a similar solution to our earlier example. Now let's look more closely at an individual channel. 2.4 GHz can only accommodate a maximum channel width of 40 MHz, since the entire range is only 72 MHz total. The wider the channel, the more throughput capability, which means potentially faster Wi-Fi. This, however, comes with a price, as the wider each channel becomes, the fewer channels you have, and moreover, the fewer non-overlapping channels. This raises the likelihood of adjacent channel interference occurring. In most networks, channels are generally kept at a maximum width of 20 MHz to increase the number of non-overlapping channels we can work with. But as mentioned, we are sacrificing potential throughput to do so. If you plan on using 5 GHz or 6 GHz with 80 or 160 MHz channels, you can get great speeds, but make sure you aren't near other networks or take care to properly plan out your channel selection. With 6 GHz, greatly increases the available space and allows the use of 160 MHz with less chance of overlap, so you can take advantage of its speeds. Like many access points, Sophos APs can be configured with automatic channel selection. The AP will detect the channel with the least traffic and switch to that channel. This is convenient in simpler setups such as home or in an office with few APs. But in high-density environments that deploy many APs, it's recommended to statically assign channels to ensure APs aren't constantly switching. Next, let's talk about the needs of your own network. When planning out the design of your wireless network, you need to determine the requirements of applications used on the network, the number of simultaneous clients, the types of clients, areas to be covered, and power availability. Every application has its own throughput requirements. For example, video streaming has a recommended bandwidth of 5 megabits per second for 1080p video and 8 to 20 megabits per second for 4K video. VoIP has a minimum required bandwidth of 100 kilobits per second up and down, but 3 megabits per second is recommended. This may not sound like much, but if you have 50 users on Skype calls at the same time, you need at least 150 megabits per second to meet the recommended throughput. So take note of what applications will be in use and make sure to find out the throughput requirements. Always ensure your network can handle more than what's required. More bandwidth will result in fewer frustrated users. Most networks have more than one user, so knowing the number of simultaneous users on your network is extremely important. Wi-Fi is a turn-by-turn system. Each device takes turns transmitting and receiving data. So if you have 50 users on your network, they're all taking turns sending and receiving data, even though it's seamless when deployed well. Next, you need to know the types of clients in your network. Devices use technologies housed under the 802.11 protocol suite, as seen here. Each standard of the protocol supports different bands and speeds. 802.11b, A, and G are older wireless technologies and have the slowest transmission speeds. Meanwhile, 802.11ax is the fastest and supports 2.4, 5, and 6 GHz bands. Please be aware that speeds listed are theoretical throughput and will differ greatly in real-world scenarios. Many modern devices use 802.11n, which supports both 2.4 and 5 GHz and is backwards compatible, but not all devices. So it's important to understand what the devices in your network require. If an access point is broadcasting 2 SSIDs on 2.4 and 5 GHz bands, it's quite likely one of those bands would be preferred. You may run into the problem where all devices connect to and congest the 2.4 GHz SSID, while the 5 GHz SSID is sitting idle with no connected users. So when deploying, you can enable a setting known as band steering. This will direct or influence any 2.4 or 5 GHz clients to use their most optimal frequency. Wireless devices can also use multiple radios to transmit more data through a process called MIMO, multiple in, multiple out. For example, a laptop can have up to 3 radios, whereas a smartphone usually only has 1 or 2 to conserve power. Looking at 802.11ac, we can see with one spatial stream or one radio on a 20 MHz channel, the max bandwidth is only 87 megabits per second. But for 3 streams, it's 289 megabits per second. So for a wireless device with only one radio, even if you're using 802.11ac, your maximum throughput for that device is only 433 megabits per second if using an 80 MHz channel. If you deploy many access points, you likely can't use 80 MHz channels, as this limits the number of non-overlapping channels available. You'd more likely choose 20 or 40 MHz channels, which means those devices can have a maximum throughput of 87 or 200 megabits per second, respectively. So no matter how fast your access point is, the network is only as fast as the clients that use it. Next, it's important to identify the coverage needed in your environment. Make sure you note the areas that need heavy coverage. For example, if most users are connected to one section of an office, the APs in that area may have significantly more simultaneous clients to them. You may need more APs in that area to distribute the traffic, and this will require more planning. It's best to limit the number of simultaneous clients on each AP to 30. Sophos APs have been tested with 60 devices connected at once, all transmitting data with little degradation. But each network will vary depending on applications and environment. Another important thing to keep in mind is the cross-channel interference from other APs. In most cases, this comes down to the fact that all APs transmitting at 100% power, which is often not needed in a high-density environment. Lowering the transmission power can significantly improve or eliminate cross-channel interference. We'll talk more about ways to determine this in the next parts of the video. In addition, be aware that different building materials can affect wireless signals significantly. Drywall and insulation block far less signal compared to thick concrete. However, in some parts of the world, there may be metallic coating between the drywall and insulation that blocks wireless signals significantly. If your site has wood or metal covered walls, this can seriously impede the signal depending on the material thickness. So keep these in mind when planning and find everything in your environment down to the wall's material. Help plan this through site surveys prior to deployments or experiencing network issues. Sophos access points can be powered in 2 ways: power over Ethernet, or PoE, or DC power. Some models can be powered through both, while others through PoE only. Be sure to check what your specific APs require. In addition, determine the infrastructure your site has available for PoE to make sure this is supported. The best way to plan your deployment specific to your site is to perform a site survey. There are 3 types of site surveys: passive, active, and predictive. Passive site surveys are listening surveys. They don't send any traffic out to the network and simply monitor radio frequencies in the area. This can detect other APs in the area, their signal strength, the channels in use, the signal to noise ratio, and other useful information. This is the most common type of survey because it's simple and doesn't require any APs to be installed. There are many applications to perform passive surveys. You can even download free apps on your smartphone. However, smartphones aren't designed specifically for surveying and may not give you the most accurate response. Active surveys are much more in-depth. For an active survey, you send and receive data on the network to get exact measurements. These are done to deploy and troubleshoot wireless networks as you measure data like throughput rates, as well as all the information in passive site surveys. When actively surveying a site, you typically create a wireless heat map to visually display the radio frequency strengths. Heat maps are useful because you can really identify where your problem areas are. Predictive site surveys are a simulated site survey. For example, in Sophos Central Wi-Fi, you can upload an image of a 2-scale floor diagram and place simulated access points to predict placement. Since you put an exact distance scale, this can give a good representation of access point range in your site. You can use many tools to do this, but remember, a simulation can only show range. It doesn't account for factors like building materials and interference. All 3 types of surveys are useful, and there are numerous tools you can find online to perform them. Now, let's talk about some other considerations direct from Sophos support engineers. If you find that there is a section of your site where devices AP hop, Either increasing the transmit power for one AP or decreasing the transmit power for the other may be an acceptable solution. If you use Sophos Central Wireless, ensure there is no web filtering or HTTPS inspection applied to the traffic destined to or originating from an AP. This can cause problems with registration for Sophos Cloud Wi-Fi. Depending on your situation, you may wish to leave only specific ports open or limit access to only the required destinations for strict control. In either case, we've linked some resources in the description with further detail to help you. Be careful when adding SSIDs, as this can increase the management frames for your AP to handle, which may impact performance. Each AP can handle a maximum of 8 SSIDs, including the Mesh SSID if Mesh will be in use. If you choose to use the most compatible encryption, TKIP and AES, remember that throughput and performance is greatly reduced due to TKIP's processing requirements. We suggest using AES only and to use a separate AP for older wireless clients that can only work with TKIP. Lastly, we'll talk about potential security threats and best practices to protect your network. With the evolution of wireless networks, it's no surprise that there's an increased security risk to your network. Here are some ways attackers can compromise your network. A rogue access point is any Wi-Fi access point that is connected to your secured wired network without authorization. This means that an attacker can access your network, leaving your IT assets wide open. When an access point spoofs the network name of your legitimate AP, this is known as an evil twin. This can trick users into connecting to them as they look legitimate. It can be set up and used to sniff wireless traffic and conduct a man-in-the-middle attack. An advanced attacker can even go as far as spoofing the hardware address, network name, and even the unique protection code. This is referred to as SSID or BSSID impersonation. To ensure that your network stays protected, you should follow these best practices. Turn off unneeded features like file sharing or remote access, and disable any unused ports on your network. Only connect to known networks and disable automatic Wi-Fi connections. Access confidential business data only on secured and trusted networks. Separate any open guest networks. And enable protection features such as rogue access point protection. Any APs managed by the Sophos Firewall or Sophos Central support this feature. So that covers our overview of wireless networks. I hope you found this video useful. Let us know by giving us a thumbs up on TechVids. Check out the resources for this video in the description. For further assistance, view and post questions on community.sophos.com and go to techvids.sophos.com for more great videos like this one. Thanks for watching.